Welcome everyone. Let's review gas laws. Okay, we're going to start with a review of what the gas law variables are. You should remember this from first year chemistry. So we have pressure, which is the force per unit area due to the collision of the particles with a particular surface. We have temperature, which you've seen already this year, and that's the average kinetic energy of your sample of particles. We have moles, which is the number of moles of particles we have. And then we have volume, so how much space something is occupying. And each of these we're going to give a letter to when we use them in our gas law equations. So pressure is P, temperature is T, moles is N, because that's the number of particles, and volume is V. Again, these should be familiar to you from last year. Before we get into using the gas laws, let me remind you how we measure pressure. If we're measuring atmospheric pressure, we're going to use a barometer. And a barometer, a traditional barometer, is a tube that's completely filled with mercury and then upended into a container or a pool of liquid mercury down below. And then what that results in is, as you upend it, the mercury in the tube is going to fall down and leaving just a vacuum, a little bit of mercury gas, but a vacuum up above. And it will fall until it is balanced by the pressure of the air pushing down on the outside on that pool of mercury. And once those forces are equal, then your mercury will stabilize and you can measure the height of that mercury. The higher the pressure, so the harder the air is pushing, the taller the column of mercury will be able to be supported. And that's where our unit for pressure, millimeters of mercury, comes from. However, if you're measuring the pressure of a gas in a closed container, we need a different tool, and this is called a manometer. So what exactly they look like, it depends exactly on the manometer you're using. I draw mine in this way. So they are a bulb that has a U-tube connecting to it. And in that U-tube, there is some mercury. And depending on the relative pressure of the atmospheric pressure on the outside and the pressure of the gas on the inside, that mercury, those liquid levels will either rise or fall. If you have a situation where the pressure of the gas on the inside is pushing harder than the pressure of the gas on the outside, you're going to see that that liquid level, that mercury level, will be lower on the mercury on the side where the pressure is higher and therefore higher on the atmospheric pressure side. If the gas pressure is greater than the atmospheric pressure, then you're going to add the difference in heights to that atmospheric pressure to calculate the pressure of the gas on the inside of your container. If, on the other hand, the pressure of the gas in the container is less than atmospheric pressure, you will see that the atmospheric pressure pushes down farther, and that makes the mercury rise toward the gas. And then in order to find your pressure of the gas inside that container, you'll take your atmospheric pressure and subtract that difference in height. And so in order to interpret a manometer, you need to use some logic and kind of think of a teeter-totter. Whichever side is heavier, has a higher pressure, that side will be lower. Whichever side has the less pressure, that side will end up being higher as that mercury gets pushed in order to equilibrate the force. Okay, a couple of reminders about units and conversions for units. First off, for gas laws, temperature is always going to be in Kelvin. That Kelvin temperature relates to the motion of the particles, and so that's the unit we need to use. And if you do not remember, in order to go from degrees Celsius to Kelvin, you're going to add 273. And similarly, if you want to get 2 degrees Celsius and you have Kelvin, you'll subtract 273. We're going to use a variety of units for pressure. Atmospheres, millimeters of mercury, torr, kilopascals, and psi are the ones that you will see most commonly. And you need to be able to convert back and forth between all of those. We'll do some practice in class, but you should remember how to do unit conversions from earlier this year and from last year. Volume for gases, we're typically going to use liters. Could be milliliters, but more often than not, we will use liters. And then for moles, we'll use moles. Obviously, at this point in time, you guys are fluent in converting from grams to moles, and you'll be using that. Okay, let's get down to the nitty-gritty. So we've got our gas law variables. We need to talk about how they're related to one another. And you talked about this extensively in first year chemistry. We're just going to do a quick recap here, and we'll revisit this more in class. Remember that some relationships are direct. For example, the number of particles and the pressure. As you have more particles, there'll be more collisions. The pressure will increase. Similarly, the number of particles and the volume. If you have more particles, in order to keep everything else the same, if the pressure is going to remain the same, they need more space to move in. Temperature and pressure will be another direct relationship. As you increase the temperature, the particles move faster. As they move faster, there are more collisions, and thus greater pressure. And those collisions actually happen with greater force. So double whammy on the pressure. And similarly, temperature and volume. As temperature goes up, in order to keep everything else the same, the volume has to go up because those particles are moving faster. There are, of course, also indirect relationships, and so these indirect relationships are pressure and volume. As the pressure goes up, assuming temperature and number of particles stays the same, you must have a smaller space for those particles to move within. Similarly, number of particles and temperature. If you want to keep the same pressure and volume, but you've got more particles, you have to slow them down. So your temperature has to go down. So those will be an indirect relationship. Okay, time to do the problems. There are two different types of problems you're going to see. The first of these is what I like to call a before and after problem. So for example, a gas occupies 1.4 liters at 3 atmospheres and 25 degrees Celsius. At what pressure will this gas occupy 2 liters at 50 degrees Celsius? So we've got the same gas and we're changing something. We have an initial set of conditions and a final set of conditions, and I want to find out some value. There are two ways to solve this. You can use logic, which is what we did in first year chemistry with the IFE tables. With this, you're going to take a look at what changes are going on in your system and think about what impact they'll have on the variable you're being asked about. So for instance, here my volume is going to increase and I'm asked about the pressure. If the volume goes up, the pressure is going to go down. But the temperature was also changing and the temperature increased. And if the temperature increases, that would increase the pressure. And so what you'll do is you'll take your pressure value and then you'll use your volume and your temperature as factors to determine how the final pressure is going to change. Since I have two different variables that are changing, I'm going to have two multiplication factors, and I'll do the volume for the first one. For the volume, as the volume goes up, the pressure should go down. So the smaller volume will go on top and the larger one will go on the bottom. So when we multiply, we'll get a smaller answer. However, for temperature, I want the pressure to increase as a result of that temperature change. And so I'll put the larger temperature on top. And then when I multiply, the value I get is the new volume, or excuse me, the new value for that pressure. A couple of things to note. First off, make sure you're converting your temperatures to Kelvin. And secondly, if there's any variable that doesn't change, you can just ignore it. It's not going to have an impact on our final value, and so you see I drew a line through n and didn't worry about it. The second option to solve a problem like this is what's called the combined gas law. This is a variation on the ideal gas law, but instead of just looking at one gas, it compares that same gas before and after, and it has the form P1 V1 over N1 T1 equals P2 V2 over N2 T2. The downside to this equation is not on the AP equation sheet, but I will show you how this equation comes about, and you can actually derive it from information that's on that AP equation sheet in case you forget it, if this is the route that you choose to take. But once you have this, you're plugging numbers in. Again, anything that doesn't change, you can cancel out. So in this case, that's going to be the number of moles. Either method you choose is going to get you to the same place, so pick the one that you're most comfortable with. The second type of gas law problem that you're going to see is what I call a one moment in time problem. And for these, we'll use the ideal gas law to solve. So an example is, say, nitrogen gas. It's in a 2.3 liter container. You've got 32 degrees Celsius for your temperature, 4.7 atmospheres. How many particles? In order to solve this, you need to remember the form for the ideal gas law. PV equals nRT. You will need to know the value for the ideal gas constant. This is on the AP equation sheet, so you don't need to memorize it, but you do need to take note of the units that you are using. So the form I prefer to use is 0.0821 liters atmospheres over mole Kelvin. Because we have one equation, all the units have to match. In this type of problem, your ideal gas equation must define the units you use for the rest of the problem. So you're going to have to convert everything into the proper units before you use the ideal gas equation. Once you've made any necessary conversions, you can solve the ideal gas equation for the variable you're looking for, and in this case we get 0.043 moles of nitrogen gas. One final note, just a term that you need to know, and that is STP, or standard temperature and pressure. This is 1 atmosphere and 273 Kelvin, or 0 degrees Celsius. It doesn't actually matter what units you use for that standard pressure and standard temperature, but make sure they're consistent with the problem you're working with. But you need to remember that STP is 1 atmosphere and 0 degrees Celsius. So we'll certainly practice more with all of this, talk about the details, have you guys apply it once we get into class. Hopefully this has refreshed your memory about the units and the variables that we use for the gas laws, as well as how to solve different gas law problems.